Good morning, everyone. Today is March 4th, and we have another Friday seminar. Thanks, everyone, for joining us for this seminar. And also, it is a hybrid meeting. There are some online people that have joined us. The today's presenter is Julie Bloxson. We are honored that we have her here. She is from Stephen F. Austin University, and the title of her talk is Potential for REEs in Large Evaporitic Bodies, Examples from North American and Phanerozoic Salt Bodies. Without getting into her bio, I would like to highlight the next presenter in March 11. It is by J.P. Brandenburg, and the title of the talk is Subsurface Modeling for Environmental Remediation. So the bio of a little bit about Julie. Julie received her Bachelor of Science in Geology from the University of Akron in 2008, where she focused her undergrad research on core analysis of tidal rhythmite deposits associated with Pennsylvania coal seams with the Appalachian Basin. She received her Master of Science in Geology from Kent State University in 2012, studying the Grimsey Sandstone Clinton Sands in Eastern Ohio. This project focused on using a combination of core and well log analysis to extrapolate porosity and permeability across a county and determine the controlling factors of porosity permeability in these tight gas sands. Then she received her PhD from Case Western Reserve University in 2017, focusing on the Utica shale and controls on deposition. Julie continued this work at the Ohio Geological Survey, working within the Energy Group on various subsurface mapping projects that focused on salt deposits, carbon sequestration, and unconventional resources for 2 years. She is currently an assistant professor at Stephen F. Austin State University since 2018 and heads the East Texas Core Repository at the Science Research Center, where she has created the Core Lab on campus. This facility focuses on non-destructive core analysis and correlates core data to well log data for better subsurface analysis for natural resources and energy-related issues. Her goal for the facility is to allow students to gain the necessary skills for industry and research, and to facilitate a connection between local industry and academia for future research. And finally, currently, she is focusing on critical minerals and REEs in evaporites and shales across North America, and characterizing conventional reservoirs for CCUS and EOR. Without further delay, let's invite Julie to take over the stage. Thank you.
Okay. Are you guys good now? Yes. Okay. All right. Well, thank you. I didn't realize you were going to read that whole thing, but so today we're going to talk about it's a culmination of work we've been doing over the last few years. We've been looking at a couple of different salt bodies. So we're just going to overview kind of what we've been finding in them. This is work with the Ohio Geological Survey still, with BP actually, and then a couple of my colleagues at SFA also. So what exactly are critical minerals? So those are critical minerals is anything that's deemed by the USGS as being essential and necessary, but there's a potential for supply chain disruption. So right now, especially with everything going on in Russia, if there's anything going on in China, things like that, those could potentially be supply chain issues. Really, they call them critical minerals because they are in mineral form. And when you start looking at what they're looking for, usually there's specific elements in there. And that's really what we're going to talk about today, because that's what I'm able to measure is some of the elemental compositions. So there are a total of 51 different critical minerals. This was just updated in 2021. So anything that's highlighted in purple has been deemed by the USGS as being a critical mineral. Some of these may seem, some of them are very specific. So like carbon is actually looking for graphite. Some of them also have been deemed as critical by IEA. And these are more for potentially up and running for renewable resources. So they can span from anywhere from lithium all the way down to lithium, and they come in a variety of different forms, really. So what exactly are they used for? This is kind of why we need to start looking for some of these. So if we're looking at them for clean energy technologies, a lot of these are going to be needed and are absolutely necessary in order for our quote unquote transition, right? We need increased amounts of copper for PV, wind, a little bit for hydro, bioenergy, et cetera. If we start looking for lithium, we're going to be needing more for any of our battery storage, right? Chromium is going to be needed for wind and hydro. Zinc is going to be needed for wind, hydro, CSP, a little bit for bioenergy. And aluminum is going to be another really big one too. So that's not necessarily on our critical mineral list. However, the IEA is also deemed as being absolutely essential in order for our renewable transition to actually happen. So they aren't just used for renewables. Really, we use them for all of our transmission lines. So copper and aluminum are needed in order for relay any of our electricity. Neodymium is used in magnets, it's used in lights, it's used in batteries, polishing, and catalysts. Scandium is used in our TVs and in our if I could talk properly, fluorescent lights. There we go. We use PM in watches and pacemakers. And even still, the potassium and potash is used for fertilizers. So right now, there's been this really big focus on these critical minerals for the renewable transition. However, these are going to be needed for everyday life too. So any way we look at it, we're going to be needing these minerals. And really what we need to look for is a domestic source. So some of the supply chains, this is some of the supply chains for select minerals needed for those clean technologies that they keep focusing on. This is again from the IEA report in 2021. And so if we look on the mining and processing side, a lot of it is coming from China, right? We have very few resources that actually come from North America. However, on the use side, China is using a lot. The European Union and US are going to be the biggest, they have the biggest demand. So while we want to use these, we aren't the ones supplying ourselves with these. So that's kind of where we come into play. So the search for REEs and other critical minerals, so rare earth elements and other minerals. Traditionally, it's done looking at hard rocks through mining, through either strip mining or a little bit of subsurface mining. The thing to keep in mind, particularly with the REEs, they're called rare earth elements because they are rare. They are usually in the ppm, hundreds of ppm to maybe thousands of ppm concentrations. So there's very little in these bodies and they need to process them. There's also the potential for finding them in shales. So this is some of the work that we've been talking about. We're potentially looking at Eagleford. Ashley and Randy have been looking at it from the Dunkard Shale up in the Appalachian Basin. There are metals that are naturally deposited in these shales. So if we're targeting these shales anyway for unconventionals, why not use the waste products, right? Why not use those cuttings and create something valuable out of it? There was just a talk, it was earlier this week actually from, I think it was the Oklahoma Geological Society or Tulsa. They're looking for lithium in the Smackover brines. So, I mean, there's other, again, waste products that we would normally deem as being wasteful and that we would just have to dispose of. Really what we're finding is there's other potential sources too. And then in 2017, DOE published a report actually looking at coal. So they're finding lithium and other REs in coals and their associated brines and their associated underclays actually. The issue is just trying to get it out of there, right? So another potential spot is actually looking for critical minerals in seawater. They've tried to take lithium, gold, et cetera, out of seawater before. The issue is that the ones that we really want are in the parts per thousand concentration. These are really, really small concentrations. So in order to actually extract it from seawater, it is uneconomical. However, they're there. We know that they're there. So if we find them in seawater, what about evaporitic bodies then? Why not have nature do the concentration itself? So the first thing we set out to do is actually look at some modern day analogs. So Searles Lake is in California, it's in Death Valley. It's known for evaporitic minerals. It's currently being exploited for salt, borax, gypsum. It's this arid enrichment lake. It's everything. It's just like this perfect little system. It actually has solutes being sourced from two different spots. It's being sourced from the nearby highlands. It's also being sourced from some subsurface springs that are coming in. So it's creating this very rich environment that has really great potential. So we had some hopper crystals. We actually had some beautiful salt crystals from Searles Lake, and we tested them just to get an idea. And really what we're finding when we're looking at our bulk elements, we have obviously an enrichment in chlorine, right? It is a salt. But when we start looking at some of the other trace elements in here, we're finding that we're actually having increased levels in vanadium, titanium, a little bit of uranium. But when we start looking at the REEs, we're actually finding increased amounts in neodymium, praseodymium, cerium, lanthanum. We're not really finding any Scandinavian and yttrium. However, these values right in here, so this gray one is coming from the underside of this piece of, the underside of this, whereas the blue one's coming from the crystals and this orange one's coming from this dark pink mass right in here. So what we're finding is we do have an enrichment of rare earth elements in this modern day salt. So what about other evaporitic bodies? So this system is very small, very enclosed. We start looking at subsurface salt bodies, such as the Louann, the Salina, et cetera. These are extensive. The Louann's up to 4 kilometers thick, covers most of Texas and the Gulf Coast region, right? It's a potential source, okay? What about those? Are we gonna find them elsewhere? So we used a combination of cores and cuttings. We have 4 sets of samples that came from across the United States. We have the Salina Group. It's from Ohio, way up in here. This is part of the Appalachian Basin. We have the Permian Hutchison Salt right in here in Kansas. We have the Permian Salado Salt from West Texas. And then we also have some Jurassic Louann Salt from offshore. So we used a handheld XRF. We crushed, sieved, and packed some of the samples if they were either cuttings or hand samples. Sometimes we ran them straight on the surface of a hand sample, and the other times we would run it straight on the surface of a core. Because that is one thing we want to try to do is try to preserve the core. So when we ran it on the surface of the core, we would take a small piece, crush it, sieve it, pack it, and just compare results to make sure that they were the same, and they were pretty close. We can do anywhere from magnesium through uranium using our handheld. Really, we focused on the critical minerals and also those REEs here at the bottom. So anything highlighted in this green and these blues. We then went through, we ran a couple on XRD just to verify some of the mineralogy that were coming through. A lot of these studies had multiple focuses. It wasn't just looking at the REEs. So some of them had, so with the Louann, we were looking at the suture zones to try to get chemical composition. The Salina, we were looking at mapping and kind of the distribution of the minerals too in there. It was an update to another study. And then we also went through and we did SEM to kind of look at the crystal structure too. So the Permian Hutchison Salt in Kansas. This is a halite interbedded with gray-black shale. It has bedded gypsum and anhydrite. All of these you're going to notice are not pure salts. A lot of these have the cyclical deposition to them too, which is just kind of when we're starting to evaporate off of any of the water, whether if it's in a lake or if it's in seawater, it actually creates this very cyclical sequence of events. There's certain things that precipitate out at certain times. With the Permian Hutchison Salt, there's actually conflicting studies. Some people say it's marine, some people say it's continental. I can't really say one way or the other based upon what we're doing here. We were looking really at the trace elements in here. So this is currently, So this has been known to be a salt body for quite some time. It's not that deep. It's usually about 600 feet to the subsurface, and it does outcrop out, well, it used to until it was dissolved off. There's shallow brine pools for wildlife that have been using this for way before we've been here. Currently it's being mined. That's where our samples came from right here in the Hutchison mine. It's used for road salt, feedstock, oil well mud. So it already has uses. However, we could potentially see about some of the other uses too. When we start looking at this, so this was a hand sample taken from the mine. Some of it's white with either organics or clay minerals in here. Some of it's red. This right here has organics. That's what these blacks are. So when we take this and we crushed it and we were running it, again, what we're finding is it's mostly salt. That makes sense, right? We do have some sulfur enrichment in here. This is the anhydrites coming in. But when we start looking at the trace elements, we're actually finding increased levels of magnesium, barium, which is kind of interesting because some of these will be contaminations from the drilling fluid. However, this is a mine, so there is no contaminations from drilling fluid on this one. So those are naturally occurring. And then our strontium, one of the samples actually reached up to 7,000 ppm in the salt body. When we start looking at the REEs, our nudidium's up in the 450 to 600 parts per million range. Praseodymium is around 250 to 400. Our cerium is between about 175 to a little over 200. And our lanthanum has an enrichment too. What we're going to see is with the scandium and the yttrium, we're not finding them in the salts. I don't think we find them in any of the salt bodies. When we move to the Permian Salado Salt in Texas, so it's about the same time period, just a little further south, or really towards the west, based upon paleogeographic reconstruction. During this time, we have withdrawal of the inland seas that covered much of the region during Pennsylvania. So really what we're doing is restricting some of this area. It's hot, it's arid. We actually have abundant tidal flats. So this is actually going to give our Salado Salt a lot of that red color because we have a lot of these red muds that are depositing at the same time, coupled with these salt beds. So this was up on the Central Basin platform. So where our salt came from specifically is over in Pecos County. When we're looking at it, it's bedded potassium-bearing salts. There's a lot of clays and organics that are coming with it throughout. When we start crushing them, we can really smell all that organic material actually coming up too. The other interesting thing about the Salado, which we didn't do a fine enough resolution for it. We did about every foot or so sampling on this set of core. You can actually get down to centimeter scale cycles in this. You can see these little pulses of where we're having fresh water come in and kind of refill in the basin in arid conditions back and forth. The Salado can be upwards of about 1,300 feet, so about 400 meters thick. So it's nowhere near as thick as the Louann. However, it could potentially be another source. It's also much more shallow. So a lot of this is going to depend on if this was ever to become a big thing. So with the Louann, a lot of them tend to be deeper, and a lot of them are used for NGL storage because you kind of need that depth to keep that pressure gradient on there. However, some of these might just be easier targets because they are shallower. So this one we had a core. We measured it at a foot interval. This is a core that we have in our core repository. We used a handheld XRF. So when we're looking down it, we're finding that it's mostly salt. It's actually not quite pure sodium chloride. The amount of chloride that's in there is a little too high to be coupled just simply with the chlorine. But what we're seeing as we're going down, we actually have these little cycles of a siliciclastic input as we're coming back and forth between salts and siliciclastics. So we have let me back up a minute. So our chlorine, our silicone, and our calcium are going to be our siliciclastic input. Our chlorine's obviously our halite, and our sulfur is going to be our sulfates coming in. So we have this constant back and forth. We have a little bit of cyclicity over here, but really what this is just showing is we have salt with clay and salts being included in there. When you look back at the core, it's exactly what we have, right? What we have in here is that all these darks in here are just these red muds that are coming in. We have periods where we have a little bit cleaner salts coming in too. So when we start looking at some of the trace elements, we have increased levels of barium in here. We do actually have a consistent amount of magnesium coming through. It's about 300 ppm throughout the salt section. Our chromium has spikes, and I don't have an exact answer as to why. It seems to be concentrating just in certain areas, and they might be associated really with the clay inclusions. The strontium and zirconium, as we're coming through, again, we have these spikes that are coming through. Those are known to be enriched in clay bodies. So any of these clay minerals, as they're depositing, they tend to be associated with the strontium, zirconium too in this section. And then finally, we do have a pretty consistent section of cobalt coming through, set right around 100 ppm. I don't have an exact answer, so what that's enriching in, there's not necessarily a direct correlation with any of the other elements. So we're still trying to figure that one out. So when we're looking through here, what we have, again, this is the same section we were just looking at. Some of these are gonna be correlated with some of with the clay inclusions in there. And then other ones are gonna be correlated a little bit more with the salts. And so looking at the silicone, we can see that the strontium and some of these zirconium peaks are correlating more with the siliciclastic component compared to the salt component. So not everything's enriching in the salts per se. Some of them are going to be some of the other bases that are coming in, some of the other mineralogical components too. Looking at the REEs, we have lanthanum, praseodymium, cesium, tellurium, neodymium, and scandium. What first glance is showing that lanthanum, praseodymium, and neodymium, they're correlating really well with each other. And that's actually going to be pretty consistent with the salt bodies. Those three elements are going to correlate pretty well with each other, while cesium and tellurium, they're actually going to be correlating together also. A little bit of background research I was doing earlier this week, cesium and tellurium tend to be associated with each other. So it's just kind of how they're depositing. And I feel like the salt work that we're doing kind of is further proving that too, that they tend to be together. So looking through this section, just kind of looking at trying to figure out what exactly is causing these enrichments. Is it the salt? Is it just coming in with the seawater? Or is it something else? Is it going to be one of the other phases? And so some of these are going to be correlating with the siliciclastic component, and some of them are simply going to be with the salt bodies too. So looking at some of the averages, so our lanthanum is averaging about 390 ppm. Our praseodymium is about 645. Our cesium is 24 ppm, which is kind of low, but there are certain levels that have a little bit of a spikes in there. Same with tellurium, it's about 65. And our neodymium is going to be about 110. It actually, I feel like I'm missing a number in here. So I was putting these and I'm looking at that. I'm like, that does not make sense. Our range is between 843 and 1098. So I'm missing a number in there. It's probably about 1,010. Those numbers are going to be important later when I show you some of the hard rocks that they're currently targeting right now. So lanthanum, praseodymium, and neodymium correlate together, just like I was saying. Cesium, tellurium tend to correlate together as well. So moving on to the Louann. So the Louann's interesting because of its extent, how thick it is, and currently it's a driving force for the Gulf of Mexico petroleum system too, right? During this time, we have rifting, restriction, and intermittent ponding throughout the area. The Louann is very variable, and it's not just due to the movement, but also there's people who are thinking that maybe it was deposited in certain sections. They weren't necessarily deposited together, not this giant 4-kilometer salt body. How to get a 4-kilometer salt body is still kind of being thought of. It's quite hard. So maybe they were having different subsections in here too. During this time, it's subtropic and arid. Overall, it's halite. We have some silty, sandy halite intervals in here. We have some impure halite intervals in here too. So it's still very variable. When we're looking at it at a log or in seismic, it kind of looks like this just massive salt body. Reality is when we start looking through on the cuttings and even still the cores, there's a lot of variability in it too. So we have a well from offshore highlighted here. So we actually have another well we just got and we're processing just from a little further west, and we're going to be getting a third well. This right here is the Puma diapier. And so we're going to be in that area. We're going to be correlating around here to see if we can get an idea of what's going on. So looking at the Louann, when we're looking at it down core, we can kind of do the same thing. We can get an idea of facies going down. This one, we have a much higher resolution compared to the previous one. So this is going from 6,750 feet from below the subsurface to about 21,000 down here. We can take our silicone and magnesium, and that's going to be representing our siliciclastic component. It's going to be a lot of clays coming in. There's actually some sands in here too. Our chlorine's obviously going to be our halite. Our sulfur's going to be anhydrite coming in. And then calcium is a little bit complicated, actually. It tends to correlate a bit with the siliciclastic component, and it tends to correlate a little bit with the sulfur component. So some of it's in anhydrite and some of it's in clay minerals in here. So it's not exact one-to-one. So going through, we can kind of divide this up. So one interesting point about this study was that we were trying to identify the suture zone where these two salt bodies collided and kind of get an idea of composition in there too. So the fact that we're looking for rare earth elements also in here was it was almost a byproduct. Once we started stopping and thinking about it, particularly with some of the other work we were doing, we're like, there must be something in here, right? So we can go through and kind of look at and identify the different facies. So at the top, we have Pliocene, Miocene shales. We have the Louann Salt, and below it, we're at the Miocene. We have some more shales at the base. Right in there, that little section is actually our suture zone. It's consisted of quartz, mica, and other clays, and there's actually quite a bit of hematite in there too. Coming down, we can look at the trace elements also. We have barium, magnesium, chromium, strontium, zirconium, and cobalt. Some of these do look like they correlate well. This right here, let's put up our facies. So this right here is our suture zone, right in here, right? This is gonna have a different composition going through because at this point, we have this salt body that's coming through, and it's actually mixing along with a bunch of the other sands and other minerals in there. So it is a different section of salt, really. Looking at some of the elements, so barium in this one is probably contamination from the drilling fluid. So I wouldn't go after that if you're simply targeting Louann for barium, right? Oops, sorry. Some of our magnesium as it's coming through, this also, looking at how it's correlating down, some of these are kind of correlating with the barium. That might also be a function of the drilling fluid too. The chromium is interesting because we have these spikes. They're not super high. They're about 75, 80 ppm. The strontium, as we're coming through, it too is correlating a little bit actually with the barium. So some of this might be in situ, some of it still might be with the drilling fluid. And then again with the cobalt, as we're looking through, we're getting about on average to the salt body, about 75 ppm. More specifically, looking at the rare earth elements, these have very similar enrichment patterns as some of the other ones. Lanthanum, praseodymium, and neodymium, they all have similar curves. They have similar trends, while cesium and tellurium, they kind of correlate too. So again, just dividing them off, we can kind of get an idea of what's going on in the different bodies. So our overlying and underlying sediments really don't have any enrichment in here. Really, everything's coming in with the Louann in here. So overall, and these ones are a little bit more accurate, I promise. So our lanthanum is about averaging at 111 ppm, 112 for praseodymium. Our cesium overall, because we have so many spikes in there, we have so many zeros. We have points where we have some and we don't. It's 8. Same with tellurium is 23, and neodymium is 214. Scandinavium really doesn't have any enrichment in these salt bodies. So some things to keep in mind as we're going through is that it's not really consistent. So in the Salado, we saw one of them was consistent down core. The rest of these are sometimes we have peaks and sometimes we don't. So one thing we do need to understand, and we're working on, is why. Why is it not consistent? So our last study is the slurry and Salina Group. This one actually has the most detail. This is the work I started out when I was at the Ohio Geo Survey, and we continued it here. So this is a little bit older. It was deposited in the Appalachian Basin. So during this time, we had, it doesn't show it well in here, but really we have we have an arch, we have a Cincinnati arch in the Michigan basins up in here. There's these periods of sea level withdrawal, and everything is just this constant back and forth. So we have periods of restriction and then periods of where the basin's opening up. So we have a lot of cyclicity in here. These are nowhere near as thick as the Louann. The salt beds, the maximum is about 120 feet thick in here, but we have a lot more individual salt beds in here. So these are deposited in Sobcuts Salina to subsea conditions. This is opening and closing of the basin. Also, this is going to span into the Michigan basin too. Sometimes there's spillover as we get. So it's not just the Appalachian Basin, but we're getting multiple, and they're the same bodies during the same time period. When we're looking at this in a well log, we have, again, multiple salt bodies interbedded with dolostone, anhydrite, shale, and siltstone. This is a lot of cyclicity in here. The way that they divide this, so they start at the A at the base, B, C, D, E, F, and G. And we would go through, and we could actually correlate a lot of these thin beds across the state. And so that was one goal of this study, was actually a subsurface study using well logs to see how much reserves were still left in the salt body. Because they do mine this for road salt. Morton is up here, they brine it for table salt. So it is used for a couple of different places, for a couple of different resources. One of the thickest beds are up here on the top in the F section from F1 to F4, just depending on where you're at. Those bodies are going to vary in thickness, but they do get upwards again of about 120 feet thick for the thickest consistent body. So this was a core mapping study. We're not going to show you the maps. I just don't have time. They're absolutely lovely, honestly. I had a lot of fun mapping them. Michael and I went through and did these. But it was also, so we were evaluating the resources, but then we were also evaluated depositional environment, because this is really where some of the deep water thoughts of salt precipitation were coming from. When they were initially studying this in the 70s, they were saying that this was deep basin, deep water, everything was just precipitating out in situ. Really, I'm gonna, I guess, spoil it, but when we're looking at the core, it's not deep water. That was one thing in the 70s, they weren't looking at core, they were doing simply from wire-light monks. So we had a core, we did XRF, XRD, and SEM on it, did a whole bunch of mapping, which we're not gonna go over. So the Salina Group, when we're looking at the core, it's actually just not pure salt. It's not pure white salt either. There's a lot of variability in it. So we have anything from white to yellow. We have some of the grays, but really the grays are organics that we included in here. And then we have this lovely red salt coming up through here, which when we were doing this was one of the first times the red salt was being documented, because on the well log, it actually shows up hot. So they couldn't tell it was a salt. So it ranges in coarsely crystalline, it's overall coarsely crystalline. We have those organic inclusions, a lot of different colors. We have that dendritic shale coming right through here, which is showcasing that we have siliciclastic input, everything's evaporating off and kind of being included in there. These are beds and fracture fills. So this is a secondary process right in here. Looking at it in SEM is actually quite interesting. So we have two different overall crystal habits in here. We have something called a chevron, which is what this is right in here. So we have these little salt crystals. So you can imagine like a cube, and that's its side, and it's just like going backwards, right? But then we also have what they call a mosaic pattern down in here, coupled with salt precipitating out in pores and fractures. So when you start reading through the literature, they state that the chevron pattern actually means it's primary deposition, that it hasn't been altered actually. This is how it's deposited during the Salina times. However, this mosaic pattern coupled with this salt precipitating out in the pores and in the fractures is actually secondary, that it has been reprecipitated out since deposition. So we're finding this in the same core, a couple 100 feet apart. However, some sections have been altered and some sections have not been. We also have anhydrites in here. I know this talk is about salts, but really what we're finding in these is we have enrichments in everything as we're going through. These are dark gray, they're black, they're massive. We occasionally get fossils in here, which is interesting. And then as we're going through, sorry, do you want me to go back? So yeah, this is a little fossil right in here. This is the only one I found in here. for something that's supposed to be deep water and absolutely, sorry, I was going to say some choice words and I probably shouldn't. An absolutely terrible place to live because it's supposed to be this super saturated, just environment with nothing in there. We're actually finding a lot of potential life in here. So we find these fossils. As we're going through the dolostone, we find algal mats in here too. These are buff to gray. We actually have anhydrite growths coming in here too. So that's what's happening right in here. We have, so all these are algal laminations right in here. That's what all these are. We have some mud cracks. We have oil staining happening throughout these, which is kind of interesting to think about. But if we're having those organics being included in the salts, I mean, it could just, everything just kind of pieces together. Also, as we're looking through these, so there's some more anhydrite growths coming in here, but we also have pyrite inclusions. So this is dolostone. This is an anhydrite growth coming through here. And then we actually have pyrite being, we have pyrite forming in the center of this anhydrite coming through. Some of these sections we are actually partially dolotomized. So looking at the anhydrite growths, so these are forming, so we have deposition, we're in shallow subsea conditions and everything starts evaporating off. And so as it's evaporating off, those anhydrites are actually growing out. So when we look at it in core going down, this is what they look like. The black is our anhydrite growths and this, this gray color is going to be our dolostones in here. So overall, what we're getting when we're looking at all these faces, we have this cyclical pattern of deposition. We have this evaporation, then we have siliciclastic influx, and it keeps going back and forth. Looking down at the faces, we can see the same thing. So our siliciclastic input is our silicone. Chlorine is going to represent our halite. When we're looking, our sulfur and magnesiums are our anhydrite, or sorry, our sulfur and calciums are anhydrite. Our magnesium is going to represent our dolomite component. Going through, we can then identify all those horizons, just like we do on the well log. And what we see is that we have these patterns. It's back and forth and back and forth and back and forth. Sorry, I'm just trying to wrap things up real quick. So as we're going through, we can then look at the trace and critical minerals. We have our barium component, magnesium, chromium, strontium. Going through, we can look at how these are correlating to the facies. Particularly because we have so many different facies and they're very distinct, particularly compared to like the Salado, where that siliciclastic input is just incorporated in the salt as opposed to being its own horizon. We can actually get an idea of where some of these are actually correlating. So our strontium, as we're coming through, because we do have some peaks around 4,000 ppm. A lot of them are sitting kind of low and probably around 1,000 ppm. But our strontium is actually correlating with our sulfur component. It's replacing some of the, it's replacing it and creating celestite. Our zirconiums are associated with our shales, which is, this is not the first, this is a common occurrence. As we keep going through, some of our other critical elements, though, they're not necessarily correlating with anything specific, but the other thing is we're finding them in the salts. That's this component down in here. However, what we're finding is that there's actually other enrichments, greater enrichments in the other bodies that are in this evaporitic sequence, the anhydrite, the shales, et cetera. Looking at the rare earth elements specifically. So again, we can go through and correlate based upon some of these horizons. These are also variable down core. I feel like I keep saying the same thing because that's what we're finding with all of these salt bodies. These are super variable down core. We do have correlations with each other. And again, they're abundant in the halites, but they're also abundant in other lithologies too. So looking at them, so this is chlorine and this is our REE component and they're color coded on the side. We do have upwards of about 650 ppm of neodymium in our chlorine is our highest RE component. However, in our other components, we can actually get upwards of about 1,300 ppm. And I believe if I remember correctly, that's in the anhydrite component actually. Oh yeah, anhydrite, sorry. So in our anhydrite component, we can get upwards of about 1,300 ppm. Again, we have increased amounts of these in our anhydrite component, particularly compared to our chlorine and to our salts. So our averages as we're going through, when these are, I went through, these are very specific to the salt bodies. We're about 164 for the lanthanum, 248 for the praseodymium, 13 for CS, 41 for TE, 390 for neodymium. And again, scandium isn't showing up in our salt bodies at all. So overall, okay, I just gave you a whole lot of numbers. So overall, there are variations in bulk and trace elements in these salt bodies. However, they're at similar magnitudes, really, as what hard rocks are being mined too. I'm going to show you that in a moment. So overall, when we're looking through, obviously we have abundant chlorine. We are getting enrichments in sulfur. We can see variable amounts of potassium, et cetera. Looking at some of these trace elements, though, they're varying based upon their salt bodies. So this is going to be a function of where these formation waters were coming from. However, looking at the rare earth elements, and I always find this fascinating, is although they have different magnitudes of enrichment, their enrichment patterns are very similar for all the salt bodies when we're looking at their averages. So right through in here, okay? So these variabilities are due to dissolution and arid events. They're going to be due to different sources. Some of these, particularly in the Salina Group, there's multiple basin flushing events that are actually going to be dissolving out certain sections in it. And that's just due to tectonics over the years. And then also there's going to be freshwater influxes throughout time, whether during deposition or shortly thereafterwards, when we're still having all this freshwater being able to infiltrate into the formation. So looking at hard rocks versus evaporites. ARE, American Rare Earths, has the Hollow Creek project area. It's in Wyoming. There's targeting the Overton Mountain, and I believe the Red Mountain, which is right below it, but this area right here in Wyoming. They just released a report last fall. Their total target rare earth oxide grade is looking for about 2,300 to 2,900 ppm. So those are, again, those concentrations for these rare earth elements are fairly, they don't need to be as high as some of the metals, right? The metals need to be in percentages. I just got out of a meeting last Monday for someone looking for iron oxides. They want 49%, right? They want, that's pretty high. We're never going to get that in the REEs. So these are what they found. I just went through and averaged them. So their lanthanum oxide is about 547. They're looking for 1,200 right in here. Praseodymium is about 128. Neodymium is 488. What we're finding in our salt bodies, the magnitudes are actually fairly similar. We're in the hundreds of ppm also. So that's one reason why these could potentially be a target, simply because for one, you could dissolve them out. Two, it could also be a waste product. So as they're going through and they're drilling through the Louann looking for other targets, just like with the shales, right? We could take those cuttings and potentially do something with it. There's also potential if they're dissolving them out for hydrogen storage, for natural gas storage. Most of the time what they do, they simply inject it as a wastewater. There's potential there for that too. So with that, I have a list of thank yous. Obviously I can't do this by myself. A lot of our cores come from donations. So, and also thank you guys for having me here so I can take questions whenever you guys are ready.
Thanks, Shirley, for an awesome talk. That was a lot of information and it was really good. And thank you for keeping things timely. Perfect time. We want to start, I guess, with a couple questions from in person, and then we'll try and kind of go back and forth between in person and the virtual chat if we've got any questions there. So. Does anybody here have any questions?
Hey, Julie.
Hi.
Great talk. Your lanthanides are really pretty enriched. I mean, that's impressive how much there is in your salts. Do you have plans, or have you looked at the heavy rare earth elements? And maybe I missed it because I was so focused on the neodymium, but have you guys looked at lithium in these salts as well?
So we cannot measure lithium, but that is our next step. So Jamie, my graduate student, is actually, we're going to send some samples off to have them measured by a lab. We've talked about potentially getting a handheld lib, so we can do them down core without destroying the samples also. Talking to other people It seems to be a little persnickety sometimes, so we'll have to figure that out. But lithium's next on the list for the Louann, actually. So, because that would be a huge one, because you don't need that much of lithium for it to be a valuable resource.
Thank you.
I thought that was really, really interesting. It seems like one of the most important controls on mineral distribution in the evaporites is the way that those evaporites were initially deposited, the environments. And I know a bit about the Louann and the way that that's deposited, which is quite unusual compared with other evaporites. But it seems like if we could get a better understanding of the depositional precipitation models, we could get a better way of predicting which evaporites around the world would be better for extraction of these elements.
Yeah, for sure. So with the Louann, so Jamie, my grad student, she is, so we have a couple ideas of where this is supposed to go. Currently, you guys have about a dozen different cores and sets of cuttings. So one thought is to go through and start correlating on the onshore to see if maybe we could find a horizon. It's very difficult with the movement it's done, right? The other potential spot is that we're going to have 3 offshore wells in that one diapier. So that's another, so we can see if we can correlate simply within a smaller area too. Some of the problems that I can foresee us running into, that first well that they gave us, I think they sampled every 30 feet and it was beautiful. The second well they gave us, they sampled every 300 feet. And while I'm still super appreciative of the cuttings, it's just the resolution's a little different. So we really need to start integrating core log or core data to see what we can really find. But that's going to be still really hard with those levels also. So we need to figure out deposition, see if there's something very specific. Then we can correlate that to the well log and then go from there to see if we can kind of have an idea of modeling and estimations.
I think that's going to be really challenging in the Louann. That Puma one has been remobilized quite a lot, so yeah, at least it's going to be tricky. But my point was a little different. A couple of things. They should probably have the mud that you could actually get the analyses of, so you could actually eliminate that out of your uncertainty. But the other one was, have you looked at cap rocks? Because I mean, I don't personally know a great deal about mineralogy, but there's definitely very peculiar mineralogies in some of the salt diapier cap rocks. And Katie Giles at UTEP might actually have some thoughts on that.
Yeah, I have not, but particularly because there's some work being done on RE enrichment in oils themselves. So you have that interaction rate in there and trying to figure, is it there? Like, are these REs being dissolved in the oils? How are they getting in the oils, et cetera? And so if those could potentially be a correlate, that's where I see it in my head, at least. This is, I don't think it's a one and done. I don't think it's just depositional. I think it's a multifaceted problem and how these are in here, particularly because we're looking at something in such low quantities. We really need to understand where it's coming from in order to get a better idea of how to map it in the subsurface and try to find it. So, but that's a really good point. But I have not.
But yes.
Oh, okay. I'm in my head. I'm thinking they're like all interconnected. But yeah,
they are absolutely. But I just thought to clarify.
Yeah.
Specific things on the top.
Okay.
Yeah.
Hi, Julie. Exciting research. And one comment and build on what Jill is saying. Yeah, also, with the cuttings, watch out for contamination from the drill bit itself, particularly with those chromium spikes.
Okay,
you know,
that's a good point.
I had considered those suspect. I'm really curious about this Halite Creek project in Wyoming. Are they only mining rare earths, or are they getting other metals or something out of that mine?
Reading, so I mean, we can give you guys a copy of the presentation. There's a link in there. The document's public. I think Ashley actually shared it to me, or maybe John shared it to me on LinkedIn or something in the fall. Looking through it, they're looking for the REs. Yeah, that's what they're looking for.
Hey, Julie, that was really nice. In one of your earlier slides, I thought it was really informational what you showed. you had the it was that one that had the crystal from the hopper versus the bulk rock. And I think that's a good approach because, you know, the way that these rare earth elements are going to be stored mineralogically is going to determine how we extract it. And you sort of showed in, you know, in the salt, or I think one of the salt crystals, you know, there's some enrichment of rare earths, but in the siliciclastics, there's a different enrichment. So I think it's a good thing to, you know, continually compare where the rare earth elements are bound. And then, you know, but you need the bulk analysis to kind of understand like how much is there overall.
Yeah.
So that was really good. The other question on that sort of follow up, and it's, you know, the thought of using the drill cuttings for extracting. Is there enough volume of drill cuttings that comes out of a well that, you know, would just make it economical, or is that, you know, is the extraction of rare earths still going to have to be a subsurface process?
That is a great question for Ashley, actually, because she's looking at it from some of the other mineral. So I think you guys have done some volumetrics for the shales, correct?
Yeah, mostly on the metal content. But yeah. Yeah, so on the metal content from these shale cuttings, some of the volume can be, you know, double-digit tonnage that's coming out. Okay. We haven't specifically looked at the rare earths, but that's definitely a component that should be looked at because out of each well, you can get about 200 tons of just bulk cuttings. So depending on the concentration, you can get some good values out of it.
I mean, the Louann in that one well is it was over 10,000 feet worth of section because they were targeting subsalt plays in that one. So, I mean, the Louann's pretty extensive. Some of the other ones might not be, particularly the thinner ones. So looking at the Silurian in Ohio, if we're hitting a section that only has a couple 100 feet of salt, it might not be worth it. However, the Louann with 4 kilometers worth of section might be worth it in that instance. So it's going to be very specific.
All right, let's take a second to swap over to the online chat real quick, just so that people get their questions answered as well.
Okay. Okay, so I'm just going to start at the bottom and go up. So RNail, just a thought, should be able to demonstrate elemental relationships, patterns via multivariate, multidimensional analysis, currents, minerals, lithology, and then to origination and depositional environment interpretations. So that's actually a really interesting point because with the Salina, partially because we have such distinct bases in there, they're not as mixed as some of the other salts. I actually went through and did principal component analysis on it, and it told me the same thing I was doing with the linear analysis, that we do have these enrichments in REEs and other critical minerals. However, they're not correlating with just one basis. First time I ran it, I got really mad, and I'm just like, this is not giving me my answer. What I want is this in the salts. And then I stopped and thought about it and was actually looking at the data, and it's actually showing that the REs are being enriched in any of these evaporitic sequences. So the carbonates and the anhydrites and the salts. And that makes sense because they're all precipitating out of the same seawater in that sequence. How do these concentrations compare with concentrations being mined for profit in China? I don't have an answer on China specifically, but that ARE project that's at the end, those are, I would say, similar magnitude. They're not the same concentrations. Some of those might be error in our spot too. So some of them are 0. Some of them weren't measured at certain points. So, I mean, there's also some variability in there. But I would say there's similar magnitudes to what they're mining in the hard rocks. China specifically, I have no idea.
So you can say they're about the same. And they might even be better than China's. China's advantage is cheap labor.
Yeah.
You know, these are really good numbers.
So Tristan said, I don't know if you heard Tristan, but he said that they're very similar to China, but China has cheap labor. So these are actually really good numbers for a lot of these. So he doesn't have a microphone. Is there a resource of measured REE from produced brine waters in the Permian Basin? I do not know of one, but what I've been hearing about lately is lithium. So again, there was a talk earlier this week, and I can share the link if you want to email me, and then you can find the guy. They were looking at lithium concentrations in the Smackover, and I've had students, like graduated students, and they've come back to me like, somebody's looking for lithium in my Smackover wells. Like, so it's happening all over, mostly in Arkansas, but northern Texas and up in there. I don't know about the other REEs in brine water. I've had that question before and I don't have an answer. I'd have to, for one, get samples, but you can technically measure it with the XRF, but there's probably going to be better ways of doing that, probably an ICP-MS for that one. The biggest issue is how economical is it to extract the REEs from the host minerals. I wonder, since these are salt minerals, can ion exchange reactions be used? I don't know. This is probably a question for Tristan, actually.
I don't know either. I mean, I think the answer is yes, but then you have all this extra stuff that comes with it. And so how do you deal with the junk that you don't want, you know?
I just, like, my first thought when getting into this was that they precipitate lithium from, what is it, the Dead Sea? So why can't we precipitate these other ones from these also? If we're brining them out, which is what we do anyway for NGL storage caverns, then we've already done the hard work. So now we just have to take out what we need from it. So how do you identify the algal mats in the Salina group? And is their concentration related to among the amount of oil staining? The algal mats, like, so we can visually see the algal mats in there. And then correlating them on the going down core, that's something I really need to do. I need to sit and really think through some of the correlations beyond just looking at the geochemistry, but actually going through comparing the core to the geochemistry, the hand samples to the geochemistry, to see that, because I don't have an answer. And I also wouldn't have had time to do any more today. Also, I've already taken out, I think it's scandium. I'm really sorry. I probably missaid that. They appear to be light rare earth elements enriched, but what about the heavy rare earth elements? I haven't looked at too much of the heavies. So the ones I have on here, what our XRF is calibrated to. And so we do have potential for further calibrations, but some of them, they have interferences, so they need very specific calibrations. So we'd have to go through and do them. But there is a potential, but I just don't know right now. Yes, it is a long bio. I didn't realize that they were going to read it all. I could have shortened it. I thought I was going on the website. That's my like default.
That's happened to a few people.
Yeah.
Don't feel bad about that.
Like, oh, should I did 3 sentences? That would have been easy. Came from Ohio. I like rocks. I'm at SFA.
Perfect.
Okay. So, okay. Oh, I got 2 more messages. Are we about done? I'm sorry. Oh,
no, it was just people saying they'd like to talk.
Okay. Well, thanks.
So, and perfect. We have exactly hit 10 o'clock. So this is going to conclude our seminar series for today. A reminder again, next week on March 11th, JP Brandenburg will be giving his talk. And Julie is going to be around all day. So for those of us at the Bureau who are still around, we can bug her all day about this stuff. So thanks everybody for coming by.
Thank you.